Okay, so we last left off on unit conversions of relatively simple unit sets. So in this next section, we're gonna focus on performing unit conversions on what are known as composite units. Now, what is a composite unit? Well, a composite unit is a unit of measurement that contains two or more base units. So for example, density is expressed in grams per milliliter. Volume is expressed as centimeters cubed. And velocity is expressed in meters per second. So to give an example, let's try to look at the conversion from 430 microgram per mil into milligram per microliter. So the way that you deal with composite unit conversions is you handle each unit in the composite unit individually. So we first have to identify our starting and ending unit for each of our components, making sure that we're going through the base unit. So in this case, we have the units of microgram per milliliter. And our end goal is to go to milligram per microliter. Okay. So we know on top, we're starting with micrograms, and eventually what units do we want to reach? What's our end unit goal for our top component unit? What is our end unit goal for the top component unit? Milligram, yep. And as a result, we'll be going through grams. Okay, for our bottom unit, we have 1 over milliliter. Our end goal is to go to 1 over microliter. And our base unit is 1 over liter. I like to write it as 1 over the unit to respect the fact that this unit is in the denominator. Okay, so now that we have our scheme, so what we're next going to do is we're going to identify a conversion factor containing the desired base unit and our starting prefix unit. So in this case, we're going from microgram to gram to milligram. So then, to go from microgram to gram, we know that 1 microgram corresponds to how many grams? What does the micro prefix correspond to? What does the micro prefix correspond to? What power of 10? 10 to the negative 6th, exactly right. So then, we now have our equality in place. If we're going from microgram to gram in our conversion factor, what unit will we have on top? What unit will we have on top? Grams, exactly right. So we'll have grams on top, micrograms on the bottom, and the power of 10 goes with our base unit. So here we have the conversion factor, just like we've done before. Okay, so now we're going to convert from our prefix unit to the base unit. So let's write our original number down. So we have 430 micrograms per milliliter. And we know that we have 10 to the negative 6 grams per every 1 microgram. And that in turn gives us let's write this out and let's show how the powers of 10 cancel. So we have 430 times 10 to the negative 6th gram per milliliter, which correlates to 4.3 times 10 to the negative 4th gram per milliliter. This is just to show how this would work if you were doing this conversion stepwise. Okay, so everything's pretty standard at this point. So our next step is to convert from this base unit to our desired prefix unit. So we're going from micrograms to grams to milligrams. So from grams to milligrams, we know that 1 milligram is equal to how many grams? What does the milli prefix correspond to? What power of 10 does the milli prefix correspond to? 10 to the negative third, exactly right. So then, solving, what unit will we want on top of our conversion factor? If we're going from grams to milligrams, what unit do we want on top? What unit will we have on top? Milligrams, yep. So then, in 1 milligram, we know that we have 10 to the negative third gram. Perfect. So we have our conversion factor. So let's write out our number now. So we have 4.3 times 10 to the negative fourth grams per mil. And we know that in 1 milligram, we have 10 to the negative third grams. Grams cancel, and we're left with 4.3 times 10 to the negative first milligrams. Remembering just from power of 10 analysis that 10 to the negative fourth times 10 to the third gives us 10 to the negative first. However, the only new catch in this problem is that we still have units of milliliters on the bottom that we need to work with. So we have to repeat this process for the second prefix unit. Okay, so we have 4.30 times 10 to the negative first milligrams per milliliter. Again, just to show our solution map, we're going from 1 over milliliter to 1 over liter to 1 over microliter. Okay, so then let's try and set up a series of equalities that we can use to complete this conversion. So we know 1 milliliter, we've seen the milli prefix before, corresponds to 10 to the negative third liter. Okay, we know 1 microliter corresponds to 10 to the negative sixth liters. Okay, so we have our equalities in place. However, we need to be really careful about how we set up our conversion factors. Okay, so what do I mean by that? So if we have 4.30 times 10 to the negative first milligrams per milliliter, okay? And we want to end up, so looking at our solution map, what units do we want on the bottom? What units do we want in the denominator after our first step? We're going from 1 over milliliter to what units in our first step? In our first step, what are the units in our denominator that we want in the first step? Liters, exactly right. So we need to have liters on the bottom. And in order to cancel our milliliters, where do we need to put our milliliters? On the top or on the bottom? Where does the units of milliliters go? They go on the top, exactly. Okay, and we know 1 milliliter corresponds to 10 to the negative third liter. So just in order for your units to cancel, they must be on opposite sides of the dividing line. So milliliters now cancel in this conversion factor. Okay. Let's keep going with this idea. Let's keep going with this idea. So after our first step, we have 4.30 times 10 to the second milligram per liter. So let's take 4.30 times 10 to the second milligram per liter. And now if we're going from 1 over liter to 1 over microliter, what units do we need to have on the bottom? What units do we want in our denominator? What units do we want in our denominator? So milligrams are perfectly fine. We've already done the conversion for this milligram unit. We have our desired units that we want, milligrams. And on the bottom, we need our desired units of microliters. So we're gonna have the units of microliters on the bottom, following our solution map that we made. And we know that in order for us to cancel out this unit of liters, where do our units of liters need to be? On the top or the bottom? Where do we put our units of liters? On the top, exactly. So we know that in 1 microliter, there are 10 to the negative 6 liter. Liters cancel, and we're left with 4.30 times 10 to the negative 4th milligram per microliter. Now, I often prefer to do these conversions in a one-line setup. So let's show how this would work in a one-line setup. So let's write out our number that we've started with. So 430 microgram per mil. We'll write as 4.30 times 10 to the second microgram per mil. And our end goal is to have units of milligram per microliter. That's our end goal. So just like before, we're gonna apply each of our conversion factors to cancel our starting units and introduce our desired units. So we know first, we're gonna convert this micrograms into grams going through the base unit. Then we're going to go from grams to milligrams. Now we have to deal with this bottom unit where we're going from 1 over milliliter to 1 over liter to 1 over microliter. And we know that in 1 milliliter, we have 10 to the negative 3rd liter. So we've canceled out our milliliters, and we know to get microliters on the bottom, in 1 microliter, there are 10 to the negative 6 liter. Now all we have to do is process our powers of 10, and after punching this into our calculator, we get 4.30. These powers of 10 cancel. So we get 4.30 times 10 to the negative 4th milligram per microliter. And I much prefer the one-line method if you're comfortable with it, as it saves you time, it's more efficient, and overall, it's much easier to check your work when you're performing a single calculator step. Any questions on this example? Does this make sense so far to everyone? Okay, so let's keep going now. And let's talk about a general rule. So when you're doing these conversions, you're going to choose a conversion factor containing your desired unit in the exact same location as the units in your desired final answer. Additionally, you want to choose a conversion factor containing the starting units on the opposite side of the dividing line. So there's another type of composite unit, and yes, we will be doing some more practice on this. Another type of composite unit that really shows why going through the base unit is much preferred are cubic and square units. We commonly see these when we're encountering volume. So you need to make sure to convert each component of a cubic or square unit. So for example, if we're asked how many centimeters cubed are in 150 millimeters cubed, the first thing that we need to do is we need to recognize each of the component units in this cubic unit. So for example, millimeters cubed represents millimeters times millimeters times millimeters, okay? So then we have to convert each of these prefix units of millimeters to centimeters. So in our solution map, we're going to go from millimeters cubed. Our end goal is centimeters cubed. So what intermediate unit should we go through? What is our intermediate unit? What's our stepping stone? What's our base unit? Meters, yep. But it won't just be meters in this case, it would be meters cubed to represent the fact that we're converting each of these millimeters to meters and then to centimeters. Okay, so now that we have our solution map in place, let's talk about how we'd handle this problem. So if we have 150 millimeters cubed, okay, I'm going to write this out in the long form way so we can understand what's going on here. So we have 150 millimeters times millimeters times millimeters. Okay, now if we want to, in our first step, if we want to go from millimeters to meters, let's write our equality. We know 1 millimeter is how many meter? 1 millimeter corresponds to how many meters? Ten to the negative third, exactly right. Okay, so we have our first conversion factor. So then, if we want to cancel our millimeters, if we're going from millimeters to meters, we're going to put meters on top. So we have 10 to the negative third meter per millimeter. So once we write out the units, we see that we've canceled one of our units of millimeters, but are we done? Have we completely converted all of our units of millimeters? Have we completely converted all of our units of millimeters? No. So we have to repeat this process for a total of 3 times. Okay. So instead of having to write out the conversion factor 3 times, there's a trick to this where we can take our 150 millimeters cubed, and the trick to dealing with cubic units is to take your conversion factor and cube it or square it such that you cancel out all of your prefix units. So then if we apply this cube to our conversion factor, we'd get 150 millimeters cubed times 10 to the negative 9th meter cubed per millimeter cubed. Make sure that when you cube your conversion factor, you're cubing your power of 10. So now millimeters cancel, and we're left with 1.5 times 10 to the negative 7th meter cubed. Okay, so now that we have the basic theory behind this, let's execute this from scratch once again. So we have 150 millimeters cubed. We know that there are 10 to the negative third meter in 1 millimeter. We're going to cube our conversion factor. Now, if our end goal is to go from meter cubed to centimeter cubed, what units should we put on top? If we're going from meter cubed to centimeter cubed, what units need to be on top? Centimeters, yep. And we know in 1 centimeter, centi corresponds to how many meters? What does 1 centimeter correspond to? What power of 10 does the centi prefix correspond to? Centi, looking at your table of metric prefixes, it's 10 to the negative second. Okay, so 1 centimeter corresponds to 10 to the negative second meters. However, we're not quite done because we have to cube our conversion factor because we're dealing with meter cubed. Okay, so let's now write these out as long form numbers, just so that way we can see how to handle cubing and squaring powers of 10. So this is equivalent to, after we apply our cubes, to 150 millimeter cubed times 10 to the negative 9th meter cubed per millimeter cubed times 1 centimeter cubed per 10 to the negative 6th meter cubed. So meters cancel, millimeters cancel, and we're left with 150 times 10 to the negative 3rd centimeter cubed, which corresponds to 1.5 times 10 to the negative 1st centimeters cubed. And this is how you'd handle a unit conversion involving cubic units. Does this example make sense to everyone? Does everyone understand the logic behind this process? Is there a question I can address about it? Is there a question in the solution that I can address? Are there any questions looking at? The cube does matter. The cube matters because when you cube your conversion factor, this power of 10 is cubed. And the way that you handle that is you multiply both of your exponents together. So do you notice how the 10 to the negative 3rd became 10 to the negative 9th when we cubed our conversion factor? And that's the only difference mathematically when you're dealing with cubic or square conversion factors. Any other questions I can address? Okay, let's keep going then. And I'll do another guided example. This time we're converting a composite unit. So we're taking 350 kilograms per milliliter and we're converting it to micrograms per kiloliter. So starting off, I write my unit conversion scheme. So I'm going to do this one step at a time, and I'm going to start with my top set of units. So I'm going to go from kilograms to the base unit of gram. And then once I'm in my base unit, I can go to my new prefix unit of microgram. Okay, so we've done the conversion of our first prefix unit in our scheme. Next, we're going to convert 1 over milliliter to 1 over liter, so microgram per liter. And finally, once we've converted to our base unit, we can go to our second prefix unit. Okay, so now that we have that set up, I'm going to write out some equalities. We know 1 kilogram. What does the kilo prefix, correspond to? What power of 10 does the kilo prefix correspond to? 10 to the 3rd, yep. We also know 1 microgram is 10 to the negative 6th grams. Okay, we know 1 milliliter is 10 to the negative 3rd liter, and 1 kiloliter is 10 to the 3rd liter. Perfect. So now that we have everything set up, What we're now going to do is we're going to write out our number with each of the units. So we have 350 kilograms per milliliter. And in our first step, we're going from kilograms to grams. So we're going to need units of grams on top and units of kilograms on the bottom. Okay, kilograms cancel. All is well with the world. Next, we're going from grams to micrograms. So what unit needs to be on top? What unit needs to be on top in this case? Micrograms, exactly. So we know in 1 microgram, we have 10 to the negative 6 grams. Grams cancel. We're left with units of micrograms. Our first part is done. Now, we're starting from milliliters on the bottom, and we're going to liters. So what unit needs to be on the bottom? What unit needs to be on the bottom of our conversion factor? If we're going from milliliters to liters, liters needs to be on the bottom in this case because our milliliters are in the denominator. So we know 1 milliliter corresponds to 10 to the negative 3rd liter. We're just filling in the blanks here. And next, if we're going from 1 over liter to 1 over kiloliter, we know that 1 kiloliter corresponds to 10 to the 3rd liter. Now we check to see our units cancel. Liters cancel, milliliters cancel, and we're left with micrograms per kiloliter. So processing out our powers of 10, we have 350 times 10 to the 3rd times 10 to the 6th times 10 to the 3rd times 10 to the 3rd. So adding up, that in turn gives us 350 times 10 to the 15th micrograms per kiloliter, which in turn is equivalent to 3.5 times 10 to the 17th micrograms per kiloliter. Does this example make sense to everyone in terms of the logic associated with composite unit conversions? Any questions on this example? So the power of 17 stems from the fact that if you break down 350 into scientific notation, it's 3.50 times 10 to the 2nd. These powers of 10 all add up to 10 to the 15th. Adding up our powers of 10 after multiplication, we get 3.50 times 10 to the 17th micrograms per kiloliter. Does that make sense? Perfect. Any other questions on this example?
Yeah, I'm not seeing where all of them are canceling out, not for all of them. Like where does a milliliter cancel?
The milliliters are originally in our input unit right here.
Mm-hmm.
And we have milliliters on the top. So they're on opposite sides of the denominator, so we can cancel them. And then for liters, we have liters on the bottom, liters on the top, so they can cancel out. Is there another unit that you have a question about?
That's fine. Okay, thank you.
Okay, are you sure? Is there a part that you'd like me to explain further? We'll be tackling a few other examples, and don't be shy to ask questions as well. Let's do another example just to reinforce this concept. So what I'd like you now to do is to attempt the following unit conversion. So this will be found in Canvas quiz 1.14-2. And I recommend using the assignments tab to access this Canvas quiz. I'm seeing a few questions in the chat, so let me address that. So pulling up the question, there's a question asking, how did we go from milligram sorry, I see so the question is, how did I go from milligrams to liters? Which section are you referring to in that question?
Okay, so is it milligram or microgram on top? The 1 microgram over.
Oh, that's micrograms, yes.
Oh, okay. So then how did you go from that to liters?
So think of it as if we're doing two conversions. In this first half, we are going from kilograms to microliter. Kilograms to micrograms. In the second conversion, we're going from 1 over milliliters to 1 over kiloliters. So the micrograms isn't being converted to liters. It's as if we're doing two conversions to get to our final composite unit of microgram per kiloliter. So think of it as if we just did two unit conversion problems in one example. First, we converted our kilograms to micrograms, and then we converted our milliliters to kiloliters. Does that make sense?
Yeah.
Perfect. Any other questions on this example? So you can separate these two conversions into two different conversion steps. And then at the end, all you'd have to do is multiply or divide your numbers to ensure that your units end up in the correct spot in the numerator or the denominator. I personally prefer the one-line method though, as it's most similar towards the types of conversion schemes you'll be drawing out and writing when you deal with chemical stoichiometry and mass mole conversions. Does that make sense?
Yeah, thank you.
Perfect. So let's now check to see how everyone's doing, and let's work on a problem solving example. So I'd like everyone to attempt the following conversion and convert the following value of nanograms per microliter into milligrams per deciliter. So let's take about 3 to 5 minutes to work on this example. You can feel free to enter your responses in the chat or via the Canvas quiz, and I'll be checking to see how everyone's responding. And then we'll discuss in about 4 to 5 minutes. And don't be shy to message me with questions or unmute and ask any question when you're solving this problem. And this is similar to what you'd see on a quiz. Yep, it's nanogram per microliter to milligram per deciliter. That's exactly correct. And don't be shy to message your proposed solutions using the chat feature. Don't worry about those just yet. Those are assignments that will be introduced later on in the semester. So I'm seeing a few reasonable responses in the chat. Let's get a few more responses, both in the chat and on Canvas, and then we'll discuss in about 2 minutes. And if you have any questions, don't be shy to pose them in the chat or unmute and ask them. You'd input your answer as a long form number. So no powers of 10, just the long form number if you expanded it out. So we have a reasonable set of responses via Canvas as well. We'll discuss in about 1 minute. So checking Canvas, we got a fair number of responses, both via Canvas and via the chat. So let's work through this example together and let's discuss some key features of this problem. So first things first, I'm always going to highlight my units. So I'm starting off, one moment. I'm starting off with units of nanogram per microliter. And in the end, I want units of milligram per deciliter. So you can think of this as two different conversions at play. So you can think of this as two different conversions at play. So first and foremost, we're going to convert nanograms to milliliters. So we're going to go through our intermediate unit of grams. Then once we've reached our base unit, we're then going to convert grams to milligrams. Okay, so we've completed our first prefix unit conversion. Then we're going to go from microliters or 1 over microliters to 1 over liters to 1 over deciliters. And this is our second prefix unit conversion. So now that we have our solution map in place, let's now execute on that solution map. So I'm going to write some equalities out. We know that 1 nanogram corresponds to how many grams? What does the nano prefix represent?
10 to the negative 9.
Yep, so we'll write that down. Okay. We also know that 1 milligram corresponds to 10 to the negative third gram. We know 1 microliter corresponds to 10 to the negative 6 liter. And 1 deciliter, what does the deci prefix correspond to in this case? What does the deci prefix correspond to? Deci is 10 to the negative first, exactly right. Okay, so now that we have all of our equalities set up, we're going to write out our number containing both of our units. So we have nanograms per microliter. So in our first step, we're going from nanograms to grams. So we're going to put units of grams on top and nanograms on the bottom. Remember, the power of 10 always goes with the base unit. Now, when we're next going from grams to milligrams, what units will we want on top? Milligrams, exactly. And then we know that in 1 milligram, we have 10 to the negative third grams. Okay, so far, so good. Now, my next question arises when we're dealing with a unit conversion where our prefix unit is on the bottom. If we're going from 1 over microliters to 1 over liters, then what units do we need to have on the bottom? What units need to be in our denominator in this case? Liters, yep. And we know that 1 microliter corresponds to 10 to the negative 6th liter. Okay. Finally, when we're going from liter to deciliter, deciliters need to be on the bottom. And we know that 1 deciliter corresponds to 10 to the negative first liters. So just to show our units cancel, nanograms cancel, grams cancel, liters cancel, and microliters cancel. So we are left with our desired ending units. So if we punch this into our calculator, we're starting off with 1.54 times 10 to the negative first times 10 to the negative 9th times 10 to the third times 10 to the 6th times 10 to the negative first. Okay. So adding up our powers of 10, that gives us 1.54 times 10 to the negative second milligrams per deciliter. And as we can see, our final units are those remaining Yeah, so those assignments will be added throughout the semester. We'll talk more about that towards the end of today's lecture period. Don't worry about them. They're not like homework or anything. They're assignments mainly designed for me to get a sense of how the class is engaging with the material and if there's anything that I can revise about my lectures. So they're mainly surveys. Mhm. Any questions on this example? Any questions? Yes.
Why is the 10 to the negative 9 and then the 3 and the 6 crossed out?
Because if we add our powers of 10, negative 9 plus 3 plus 6, it's negative 9 plus 9, so they cancel out.
Oh, okay, I see.
I always like to cancel equivalent positive and negative powers of 10, just so that way it's less successive math that I have to do.
Okay, thank you.
Any other questions? If not, let's do another set of examples. So in this case, we're doing a cubic unit conversion. So let's look through this cubic unit conversion. So it's asking how many micrometers are in 4.5 times 10 to the first decimeters. Okay. So we're going from micrometers cubed to decimeters cubed. So our base unit is meters cubed. Okay. We know that 1 micrometer corresponds to 10 to the negative 6 meters. And we know that 1 decimeter corresponds to 10 to the negative 1st meters. So writing out our number with our units, 4.5 times 10 to the 1st decimeter cubed, we know that we need units of meter. Oh, I have this reversed. Oops. We're starting with decimeter cubed and we're ending with micrometer cubed. Okay, so now if we need to go from decimeters to meters cubed, we're going to put meters on top, decimeters on bottom. In 1 decimeter, we have 10 to the negative 1st meter. But what do we have to do to this conversion factor? Since we're dealing with cubic units, what do we have to do to our conversion factor? Cube it, exactly. Okay. Now we're going from meters to micrometers. We're going to put micrometers on top. So 1 micrometer corresponds to 10 to the negative 6th meters. And again, we have to cube our units. This is equivalent to saying 4.5 times 10 to the 1st decimeter cubed times 10 to the negative 3rd meter cubed per decimeter cubed times 1 micrometer cubed times 10 to the negative 18th meter cubed. Decimeters cubed cancels, meters cubed cancels, and we're left with 4.5 times 10 to the 16th micrometers cubed. Are there any questions on this example? And I see in the chat we have a question about the previous example. We can certainly go back to that after we address this first question. Any questions on this example? Any questions on this cubic unit conversion? If not, let's address the question from our earlier quiz question or problem solving question.
Yeah, my question just is, how would you want us to write it down on the quiz? Because it says only numerical values are
Yeah,
accepted.
so you convert this this number in scientific notation into an exponent. So it'd be, sorry, into a decimal. So it'd be 0.0154 milligrams per deciliter. And it's just because Canvas doesn't handle scientific notation all that well when you're having it look for exact numerical answers. So you
Okay.
convert any number that you get as an output into a decimal.
Okay, thank you.
Perfect. So let's do another example. This time it's a mixture of all of the things that we've dealt with. We have a composite unit containing a cubic unit, but it's not like we can't handle that. So first I'm going to write out my units. So we have kilograms per kilometer cubed and micrograms per centimeter cubed is our final goal. Okay, so first and foremost, we're going to convert our top unit. So we're going to go through our base unit of grams. And then once we've reached our base unit, we're going to convert to our desired prefix unit. Now, just like any other unit to unit conversion, if our end goal is micrograms per centimeters cubed, and we have kilometers cubed in our denominator, we're going to go again through our base unit of meters, but note that it's a cubic unit because we started off with a cubic prefix unit. Wonderful. So now all we have to do is write our equalities. So 1 kilogram corresponds to 10 to the third gram. 1 microgram corresponds to 10 to the negative 6th gram. 1 kilometer corresponds to 10 to the third meter. 1 centimeter corresponds to 10 to the negative 2nd meter. So now that we have our equalities, all we have to do is write our number, 1.6 times 10 to the 15th kilograms per kilometer cubed. Okay. To go from kilograms to grams, we need units of grams on top. So we know we have 10 to the third grams per every 1 kilogram. To go from grams to micrograms, we need units of micrograms on top. So we have 1 microgram per 10 to the negative 6th grams. Kilograms cancel, grams cancel. We're left with our desired units of micrograms on the top. To cancel kilometers cubed, if we want to go from kilometers cubed to meters cubed, what units do we want on the bottom? What units do we want on the bottom? In our first step, when we're starting from kilometers cubed, what units do we want on the bottom in our first unit conversion? Meters, and more specifically, meters cubed. So we know 1 kilometer corresponds to 10 to the third meter. However, since we're dealing with cubic units, we take our conversion factor and we cube it. Next, we're going from meter cubed to centimeters cubed on the bottom. So we know 1 centimeter corresponds to 10 to the negative 2nd meter. And again, just like before, we cube our conversion factor. Now, as we see, kilometers cubed cancels, meters cubed cancels, and we're left with our desired units of microgram per centimeter cubed. Allow me to write this out in a way where it's clear to see how the units cancel. And so that way it's easier for us to do power of 10 analysis. Remember, when you cube a power of 10, you multiply your two exponents. Kilometers cubed cancels, meters cubed cancels, kilograms cancel, grams cancel. And if we're punching this into our calculator now, we have 1.6 times 10 to the 15th times 10 to the 3rd times 10 to the 6th times 10 to the negative 9th times 10 to the negative 6th. So same powers of 10s, we can cancel that. And that in turn gives us 1.6 times 10 to the 9th micrograms per centimeter cubed. Any questions on this example? Any questions on this example? If not, let's now tackle a problem solving session. So let's take about 5 minutes and let's work through. Yes, you'll be allowed blank paper for the tests. Yeah, that's no problem at all. Yeah, scratch paper is more than allowed on exams. I wouldn't expect you to do all of this in your head or on the computer for sure. So let's take about 5 minutes and let's work through the following two conversions. This is Canvas problem solving session 1.14-3. And make sure to enter your number as a long form decimal, and we'll discuss in about 5 minutes. And don't be shy to message your responses via the chat or using the Canvas quiz feature. And if you have any questions, don't be shy to message me while you work through this problem. And if there are any questions when solving these problems, don't be shy to ask. We'll discuss once we have a reasonable number of student responses. And don't be shy to take your time. On quizzes and exams, these types of problems should take anywhere between 5 to 7 minutes in order to stay on pace. Any questions working through these examples? I am checking Canvas and haven't noticed a ton of responses just yet, but that's okay. I'm seeing some reasonable responses in the chat so far. Let's get a few more responses before we discuss this first part. And if anyone has a response for the second component of this problem solving session, don't be shy to share it in the chat or via Canvas. I am checking both. Any questions? Checking Canvas, we have a few responses. Let's give everyone about another minute for the first component of this problem solving session. I just want to make sure everyone's comfortable with these conversions, as these are really the backbone of what you'll be doing when you tackle mass mole conversions, atom molecule conversions that are found throughout chemistry. Would anyone else like to volunteer a proposed solution for this first conversion? If not, we'll discuss in about 1 minute. So we have a reasonable pool of responses, so let's discuss this question. So first and foremost, we're asked to figure out the number of nanometers in 4.5 times 10 to the negative 9th millimeter cubed. So we know we're going from millimeters cubed all the way to nanometer cubed with our intermediate unit of meters cubed. So we have 4.5 times 10 to the negative 9th millimeters cubed. Let's now write out some equalities. We know a millimeter is 10 to the negative 3rd meter, and a nanometer is 10 to the negative 9th meters. So then, if we want to go from millimeters cubed to meters cubed, we know that we want units of meters on top and millimeters on bottom. 1 millimeter corresponds to 10 to the negative third meters. However, because we have cubic units, we need to cube our conversion factor. Now, from here, we're going from meter to nanometer, and we know 1 nanometer corresponds to 10 to the negative 9th meter. Again, cubic units, so we cube our conversion factor. So we have 4.5 times 10 to the negative 9th millimeter cubed times, and let's apply out and let's distribute this cubic factor. So we have 10 to the negative 9th meter cubed per 1 millimeter cubed. We have 1 nanometer cubed over 10 to the negative 27th meter cubed. Millimeter cubed cancels, meter cubed cancels. And overall, we have 10 to the negative 18th times 10 to the 27th. And that in turn gives us 4.5 times 10 to the 9th nanometers cubed. Does that make sense to everyone? Any questions on this example?
Wait, so that's the answer. It's 4.5 times 10 to the 9th nanometers cubed?
Yep.
Okay. And I'm sorry, how do we write that again on the quiz?
On the quiz, so you'd write it as 4, 5, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. Unfortunately, Canvas doesn't have the best tools for processing scientific notation while still respecting precision.
Okay, so the 5 would count as one of the 9s. I mean, sorry.
As one of the decimal places,
The
yeah.
decimal. Okay.
Yeah.
Thank you.
So to give everyone a little bit more time, I'd like everyone to take what we've learned from these previous examples, and I'd like you to try to apply that to this next example here. So this is the type of conversion that you may be expected to do on a quiz almost assuredly. And it's about as difficult as we can get for these types of unit conversions. And it's probably the most relevant if you have to do calculations for like biology solution prep, for solution prep in chemistry, and for expressing concentration for sure. So let's take about 3 to 4 minutes and let's work on this next example. I really want to make sure people can do these kinds of conversions involving composite and cubic units. So that way, when we move on to chapters such as covering concentration, we're very comfortable with this idea of unit conversion. So let's take a few minutes. You're more than welcome to submit your responses via the chat and via the Canvas quiz feature. I already see a few responses for this question in Canvas quizzes, but we'll give everyone a little bit more time and we'll discuss in about 3 minutes. And if you have any questions, don't be shy to message me via the chat. We have a reasonable pool of responses so far, so let's discuss this example. So first and foremost, let's write out our units. We have centigram per millimeter cubed, and our end goal is milligrams per centimeter cubed. So first and foremost, we'll convert our top prefix unit of centigrams to our base unit of grams. Then we'll go from grams to milligrams. Once that is complete, we have millimeters cubed. We need to get to centimeters cubed, so we'll go through our base unit of meters cubed. So now that we have our problem solving scheme in place, now all we have to do is write out our equalities and execute on this problem solving scheme. So we know 1 centigram corresponds to 10 to the negative second gram. 1 milligram corresponds to 10 to the negative third grams. 1 millimeter corresponds to 10 to the negative third meter. And 1 centimeter corresponds to 10 to the negative second meter. We're next going to write out our number with the units. So we have centigram per millimeter cubed. To go from centigrams to grams in our first step, we need units of grams on top and units of centigrams on the bottom. So 1 centigram is 10 to the negative second grams. Next, we'll go from grams to milligrams. So we'll put milligrams on top, and a milligram corresponds to 10 to the negative third gram. Now, if we want to go from millimeter cubed to meter cubed, we put millimeters on top and meters on the bottom. 1 millimeter is 10 to the negative third meter. However, since we're dealing with cubic units, we have to cube our conversion factor. Finally, when we're going from 1 over meter cubed to 1 over centimeter cubed, we know that there are 10 to the negative second meter per 1 centimeter, and we have to cube our conversion factor. Centigrams cancel, grams cancel, millimeters cubed cancels, meters cubed cancels. To write this out in a way that makes it a little more palatable to deal with the powers of 10, let's write it out with the units first, just for completeness sake. So remember, when you apply the cubic unit, you multiply your exponents. So as we see, all of our undesired units cancel, and we're left with 1.70 times 10 to the second times 10 to the negative second times 10 to the third times 10 to the ninth times 10 to the negative sixth. Opposite powers of 10 cancel, and that in turn gives us 1.70 times 10 to the negative sixth milligrams per centimeter cubed. Does that make sense to everyone? Any questions? Oh, wait, one moment. There was an error in adding my powers of 10. Should be positive 6. There we go. Just checking one more time. Yep. So our final answer is 1.70 times 10 to the positive 6 milligram per centimeter cubed. Any questions on this example? Any questions in solving this problem? And it's always important just to check your work in the multiplication step. This is often where calculator errors can appear. Just make sure that your correct powers of 10 are written out and that you've added your powers of 10 correctly. Any other questions on this example? If not, we'll continue on. Okay, so next we're going to talk about significant figures, and this is primarily where students lose the majority of points on their lab reports, and it's really important that you take and report your measurements and calculations to the correct number of significant figures, because significant figures are implying a lot about a measurement. So when you take a measurement, there are two types of digits. Certain digits, which are digits explicitly marked by a graduated mark or explicitly recorded on the instrument, and there are also uncertain digits or estimated digits. Estimated digits are digits not marked by a graduated mark, and generally it's the last digit in a measurement. If you add up all of your total number of digits, certain and estimated, the total number of digits reported is the number of significant figures. So for example, 50.1 has 3 significant figures because it has 3 total digits. Likewise, 30.07 has how many sig figs? How many sig figs would 30.07 have? 4, yeah. And we like to abbreviate significant figures as SF. Just for brevity. Okay, so significant figures can be thought of as the number of digits reported in a measurement. Measurements with more significant figures are more precise in general. So let's take a look at the following 3 measurements, and let's try to answer the question, how many significant figures do the measurements have, and which measurement is the most precise? So let's start with this first example. So we'll talk about rules for identifying whether a 0 is significant. For these examples, you can assume that all the zeros written are significant in this case, and they in fact are significant. So let's work through and let's look at each of these numbers, and let's try to classify and identify the total number of significant figures in each of the measurements. So 15.00 has how many sig figs? How many sig figs do we see in our first measurement? 4, yep. Okay, what about this second measurement, 2.0 milliliters? 2, yep. And 15.000 grams, how many sig figs do we have? How many sig figs do we have? 5. So in general, numbers with the greatest number of significant figures are more precise. So which measurement is the most precise measurement? Which measurement is the most precise? The first, the second, or the third? The third, right? Has the most number of sig figs. So we'll label this as the most precise, generally speaking. Okay, let's keep moving on then. So the main place where significant figures come up has to do with when you start taking measurements using graduated devices. And a graduated device is a device with markings indicating an increment of a unit of measurement. So for example, the following ruler has centimeter increments. So if we look really closely, to go from 60 to 70, it takes us 10 marks. Just showing the counting here. Okay, so then by default, we took 10 centimeters in 10 marks. I like to call these marks, quote unquote, tick marks or ticks. So 10 centimeters corresponds to 10 ticks. So then we can see that 1 tick, each of these little graduated marks, is 1 centimeter. So I didn't necessarily need to tell you that this ruler had 1 centimeter increments. You actually have all the tools at your disposal to determine the value of a tick mark. Okay, so for graduated devices, the certain digits are those explicitly noted by the graduated increments. So as we see, this block of wood has if we measure its length in the ruler, we can definitely agree it's greater than 60 centimeters, that's for sure. Okay, so we'll put a 6 down in our tens place. What do each of these little marks represent? What do each of these little marks represent? What is a certain digit indicated by these marks? Is our ones place certain or estimated? Can we clearly see the ones place indicated by a graduated mark? Yes. So we know that the length is somewhere around 64 because it's past this 4 mark. Okay, so these are certain digits. These are explicitly marked by your graduated instrument. The uncertain digit or estimated digit is estimated between the graduated marks. It's generally 1 decimal place over from your certain digits. So for example, we can clearly see that 64, it's somewhere around 64 centimeters, and we can estimate 1 more digit. Would someone like to provide an estimated digit for this wood block's length? 0.2, sure. And this last digit is our estimated digit. It is not explicitly noted by a graduated mark. Okay, so as a general rule, you can typically report estimated digits up to 1/10 of the smallest graduated mark, which is a tick. So for example, in this case, 1 tick is 1 centimeter. So 1/10 of a tick is equal to 0.1 centimeter. So we can report we can estimate to the 10th place. Does this idea make sense to everyone? So the type of graduated marks in your instruments directly correlates to the number of certain digits you can report and the magnitude of your estimated digit. Any questions on this idea? If not, let's keep going then. So let's suppose we have a few rulers. So the first ruler is just a repeat, but I'm going to show you the process that I want you to tackle anytime you look at a graduated instrument and try to take a measurement from it. So from 60 to 70, from 60 to 70, so from 60 to 70, it takes me a total of 10 ticks, 10 of these little marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, perfect. So we know that 10 ticks are equal to 10 centimeters. 1 tick is equal to 1 centimeters. And we also know that a tenth of a tick is equal to 0.1 centimeter. So we know in terms of our certain digits that we can report 64, and then we can estimate an additional digit. So we can say 64.2 centimeters. So this measurement overall has a total of 3 significant figures. Let's look at another ruler. What happens if you change the value of your graduated marks? So let's look here. So from 60 to 70 centimeters, we have 1 tick. Okay, so then 1 tick is equal to 10 centimeters. 1/10 of a tick is equal to 1 centimeters. So our certain digit in this case, is 60, and we estimate it's about 64 centimeters. So this number has 2 sig figs. So does everyone notice how changing the value of your graduated marks directly affects the precision of your measurement and the number of sig figs you can report? Does everyone see that relationship? Okay, so typically you observe variations in the estimated digit equal to 1 unit of the estimated digit. So for example, 64.2 centimeters, this measurement typically varies by plus or minus 0.1 centimeters. To contrast this, our measurement using ruler number 2, which is 64, will vary by a unit of 1 centimeter. So why does this matter? Why does this matter? Well, precision is a measure of the variability or deviation in a data set. So in general, measurements with large number of significant figures are considered more precise, as the estimated digit is smaller relative to the measurement. So if we take 0.1 over 64, we're looking at something that's roughly, just as a ballpark here, of about 0.001, roughly. While 1 over 64 is roughly 0.001. 0.01. So the relative variation in our second measurement is larger. So this second measurement has more variation and it's less precise. Does this make sense to everyone? So 64, we just estimated it. You guess and you approximate your estimated digit, just looking at where the thing you're trying to measure lies relative to the tick marks. In this case, it's somewhere between 60 and 70, but it's not quite in the middle. So I estimated it to be 64. If you said 63, 65, 66, all of those would work. And that's actually the point of the estimated digit. It has an inherent variation associated with it. There's an inherent uncertainty associated with it. Does that make sense?
Yeah, I'm still confused. What is the 1 unit of the estimated digit? Why is there a 0.1 centimeters and then 1 centimeter?
Yeah. So our estimated digit is in the 10th place in 64.2, right? And because it's in the 10th place, you will see some variation in your 10th place. So this plus or minus 0.1 is saying your value could be anywhere from 64.1 all the way to 64.3. Likewise, this value of 64 is really measured from a range of 63 to 65 centimeters. So there's an inherent uncertainty in your estimated digit. And so as a result, even though you took a measurement, you wrote down an exact set of numbers. In reality, that measurement, depending on who's taking the measurement, will inherently have this uncertainty and can vary across a range of about 1 unit of the estimated digit. Does that make sense? So this is just to show the approximate variation in your measurement. And it's based on what place your estimated digit is present in. So if it's in the 10th place, you observe variation in the 10th place. If it's in the ones place, you observe variation in the ones place. And it's just to show that there's a variability in each measurement. Did that address your question?
Yeah, okay, thank you.
So let's take a look now at a few more examples, and let's try to record a measurement on a sample graduated device. So let's take a moment and report the following length for a centimeter ruler. I just want to see the certain and estimated digits recorded properly. You don't have to worry about the plus or minus portion, just the certain and estimated digits. And this is a centimeter ruler. So let's take about 2 to 3 minutes to work through this example, and then we'll come together as a group to discuss. And this corresponds to Canvas quiz 1.15. And you really just want to make sure you're checking the value of a tick mark. Let's take about another minute and a half to take this measurement, and then we'll discuss as a group. So we see already a range of answers discussed. And I see a lot of reasonable responses as well through the Canvas app. So let's discuss this example. So first and foremost, from 1 to 2, to go from 1 to 2 centimeters, that in turn takes us 1, 2, 3, 4, 5 ticks. So in 1 centimeter, it takes us 5 ticks. Now this is a common trick that they often use in measurement labs in order to check that students are paying attention. They give the students a graduated device with slightly unusual tick marks. So then we can estimate then that 1 tick is 1/5 or 0.2 centimeters. Wonderful. So then we also know 1/10 of a tick is 0.02 centimeters. Okay, so we can report an estimated digit up to the hundredths place. So we estimate our value is somewhere between 1.4 to 1.6. I can say it's about 1.5. Yeah, it's clearly somewhere in the middle. So these are our certain digits. And then we can estimate an additional digit, and I'll put my estimated digit as 0. So this number overall has 3 sig figs. Now, of course, there's going to be some variability in your measurement. Of course, there's going to be some variability. So it can be anywhere from about 1.46 to all the way up to 1.56 roughly. So if your number is slightly different, nothing wrong with that. You just want to make sure your certain digits are clearly indicated and your estimated digits are clearly indicated.
Hey, Professor, I have a quick question
Yes.
on how do we know like whether our estimated digit would be in the tenths place, or excuse me, in the hundredths place and not just the tenths?
Because you can generally use the rule that the estimated digit can be reported up to 1/10 of a tick. So since 1/10 of a tick is in our hundredths place, our estimated digit is in the hundredths place.
Okay, cool. Awesome, thank you.
Yep. So one thing that students often run into issues with is when they look at a balance, they think, oh, it's giving me this value, I don't have to estimate anything. Well, all instruments have an inherent uncertainty in their measurement. This is also called error. Now, we don't address error analysis fully in this class, but as a rule of thumb for this class, the last digit reported from other devices is the estimated digit. Even though you're not having to manually measure between tick marks, there's an inherent variability in the last digit of every measurement. So for example, if your balance gives you the following value, 10.001, this 1 is estimated. Okay, let's keep going now. Let's talk a little bit about volumetric glassware. When you do the glassware lab, you may want to reference this page. So volume, just again, is the space occupied by matter. And here we have pictures of different pieces of volumetric glassware. Now, you'll see a lot of these in your lab box kit. The beaker is for imprecise volume measurements. It's literally just a liquid carrier. It's not designed for you to actually take any measurements of value. A burette is gold standards for precisely dispensing variable volumes. The burette is up here. It's filled with the red liquid. The volumetric flask has this little graduated mark on top. And this graduated mark is highly precise. Volumetric flasks are designed to precisely measure a fixed volume. Imagine just one tick mark that says 100.00 milliliters. You can't fill it halfway, but if you fill it to the line, it will give you a very, very precise volume. Key takeaway, don't fill a volumetric flask halfway. It has to be filled fully. And so to clarify, yes, the quizzes are graded based on attempts. They're mainly just designed as a checkup for these in-lecture quizzes. A graduated cylinder, and students often think when they take measurements using a graduated cylinder following the tick mark rules that they're pretty precise, but graduated cylinders, they're good for dispensing variable volumes with medium precision. So a graduated cylinder is up here. A volumetric pipette, and these, depending on the manufacturer, have slightly different standards, but the volumetric pipette is designed generally for precisely dispensing a fixed volume. And you can tell volumetric devices by this telltale tick mark. Does everyone see this white tick mark here? That's essentially saying this volumetric pipette is fixed, and this looks like a 25 mil volumetric pipette. So it will very precisely dispense 25 mils if you fill it to the line exactly. Finally, you have your Erlenmeyer flask, which is for imprecise volume measurements. An Erlenmeyer flask shown here is really just used for mixing things. So if you're having trouble identifying glassware from your lab kit, you can always reference this page. Okay, so let's get down to the important details for measuring volumes. So when you measure volumes using volumetric devices, you need to measure the liquid volume from the bottom of the meniscus at eye level. So this is the standard. So if you zoom into a liquid, you may notice this curvature in the liquid surface. That's due to differing interactions with the glass versus with the liquid interacting with itself. And this is known as a meniscus. For water, the meniscus is concave. If you happen to do a titration with mercury, it'll be convex. Okay, so you're going to measure your volumes from the bottom of the meniscus at eye level. So we're going to identify the bottom of the meniscus. Let me use a different color for this. Let's use red, as that's pretty bright. Okay, so here's our approximate bottom of the meniscus. Okay, let me just erase so that way it's a little cleaner. Okay, so here's our bottom of the meniscus. So then, now that we have located the bottom of the meniscus, we just take our measurement like any other graduated device. So to showcase this process, first we know from 8 to 9, it takes us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So from 8 to 9 milliliters, it takes us 10 ticks. Ergo, we know that 1 milliliter is equal to 10 ticks. So then 1 tick is equal to 0.1 milliliter. We know a tenth of a tick, which is what we can use to determine what magnitude our estimated digit will have. 1/10 of a tick is 0.1 over 10, which is 0.01 milliliters. So from that, I already see someone volunteering a measurement. So our certain digits, it's definitely greater than 8 mils, and it's definitely above or at the third tick mark. So we can definitely say 8.3, and then we can estimate one additional digit, which we can estimate as 0, for a measured value with a total of 3 sig figs. Noticing that our estimated digit is in the hundredths place, matching our 1/10 of a tick rule. Does that make sense to everyone? Any questions on this example? So let's look at another common piece of glassware. So one thing that you immediately notice if you look at a barrette, does someone notice anything odd about the tick marks? Does someone notice anything odd about the tick marks? Anything stand out about the volumes in this barrette? Yeah, so the top of the barrette is 0, the bottom of the barrette is 50. So the markings on a barrette are quote unquote upside down because barrettes measure the volume dispensed. Just like before, you read the bottom of the meniscus at eye level. So I always like to annotate. So from 30 to 31 milliliters, it takes me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ticks. So 1 mil is equal to 10 ticks. So 1 tick is 0.1 milliliter. 1/10 of a tick is 0.01 milliliter. Okay. So this first tick right here would be 30.1 and so forth. So looking at the bottom of the meniscus, what 2 tick marks is it between? Would someone like to provide me the certain digit for this measurement? What certain digits do we have? We definitely know it's greater than 30 mils. But what's our other certain digit? Is it 30.1? Is it 30.8? Note that each tick mark is 0.1 mils, but you're on the right track. Would you like to provide a revised response? Yep, there we go. So it's somewhere around 30.2. So this second mark right here represents 30.2. A common mistake students make is they read the barrette upside down, and as a result, they'd end up reporting this as 30.8 when it's really about 30.2. Okay, now these are just our certain digits. Would someone like to volunteer an estimated digit? And as our classmates have astutely pointed out, we can report one additional estimated digit, which is 5 in this case. Your exact estimated digit may vary to give a measurement with a total of 4 sig figs, where we have 3 certain digits and 1 estimated digit. Exactly right. Yep. So a reasonable measurement for the volume in this barrette would be 30.25 milliliters. You can report estimated digits up to 1/10 of a tick. Not in this case. So the only case where you have limitations in terms of what digit you can report for your estimated digit would have to do if your tick marks are an increment larger than 1 unit. So for example, if 1/10 of a tick was 0.5, then yes, we can only report 5 or 0. In this case, 1/10 of a tick is 0.1. So we have permission to report any digit that we choose in our estimated digit column. Does that make sense? So now that we've seen some examples of taking volume measurements, let's take a look at the following example. These are two examples in Canvas Quiz 1.15.1. And I'd like you to take the following barrette measurement and select which of these four options is the correct measurement for the volume in this barrette. And we'll discuss in about, let's do 1.5 to 2 minutes, as this is the first part for this two-part exercise. And don't be shy to share your responses via Canvas or via the chat. And don't be shy to type your proposed responses. I already see some participation both via Canvas and the chat. Let's get a few more responses and then we'll discuss in about 30 seconds. Okay, so let's discuss. So first and foremost, for this barrette, we know that 10 ticks are equal to 1 mil. You can manually count that. So then 1 tick would be 0.1 mil. A tenth of a tick would be 0.01 mils. We know that we're past the second. We're just about at the second tick mark. So as we're just about at the second tick mark, and barrettes are red from top to bottom, this second tick mark corresponds to 24.2. And then we can estimate an additional digit up to 1/10 of a tick, which is 24.20 milliliters. Does this example make sense to everyone? Any questions on this example? To wrap up today's session, let's take one more volume measurement, this time in a graduated cylinder-like device. So let's take a moment and let's record the following volume measurement, and then we'll discuss in about 1.5 minutes. And don't be shy to message your proposed responses using Canvas or via the chat function. We already see some reasonable responses so far. Let's discuss in about 30 seconds. Okay, so let's discuss. So again, counting from 10 to 11 takes us 10 ticks. As a result, 1 milliliter is equal to 10 ticks. Ergo, 1 tick is 0.1 milliliter, and a tenth of a tick is 0.01 milliliter. 1, 2, 3, 4, 5, 6 are certain digits. We're past the 6th tick mark, so it would be 10.6. And then we can estimate one additional digit up to a tenth of a tick. So it would be 10.65 milliliter. You can also report it as 10.68, 10.66. All of those are valid answers, as long as you're reporting the correct total number of sig figs and clearly reporting your estimated digit. Any question on this example? So with that, we'll conclude today's lecture session. We'll take a short 40-minute break and then resume for laboratory at 12:40.